Imagine a universe without light, a cosmos of eternal, unbroken darkness. Nothing to see, no plants to grow, no sun to warm a planet. Light is the lifeblood of our world, the messenger that paints our reality. It travels across unimaginable voids of space to bring us the story of the stars. And yet, this thing that we depend on for everything is one of the deepest, most mind-boggling mysteries we have ever encountered. For centuries, the greatest minds in science have asked a seemingly simple question. What is light? The answer, as it turns out, is anything but simple. It's a story that challenges the very fabric of everything we thought we knew about reality. For a long time, the picture seemed straightforward enough. Sir Isaac Newton, a giant of science, imagined light as a stream of countless tiny bullets of energy he called corpuscles. Think of it like a cosmic hailstorm, with each particle traveling in a perfectly straight line, unless it bounces off something. This idea made a lot of sense. It explained why light casts sharp shadows and how it reflects off a mirror, just like a ball bouncing off a wall. For over 100 years, this was the accepted truth. Light was a particle. Case closed. Or so everyone thought. Science, however, is a story of questioning the answers. Then, in the early 1800s, a brilliant physician and physicist named Thomas Young decided to put Newton's idea to the test. He devised an experiment of beautiful simplicity. He shone a beam of light onto a barrier that had two incredibly thin, parallel slits cut into it. If light were just particles, like tiny sand grains, being thrown at the barrier, you would expect to see two distinct lines of light on the screen behind it, one for each slit. But that's not what Young saw. Instead, he saw a mesmerizing pattern of multiple bright and dark stripes, a pattern that could only be made by waves. This phenomenon is called interference. Imagine dropping two pebbles into a still pond. The ripples from each pebble spread out and interact. Where the crests of two waves meet, they amplify each other, creating a bigger wave. Where a crest meets a trough, they cancel each other out, leaving the water flat. The bright bands of light Young saw were where light waves were adding up, and the dark bands were where they were canceling out. This single, elegant experiment seemed to prove it once and for all. Newton was wrong. Light wasn't a particle at all. It was a wave, rippling through the cosmos. The story should have ended there, with light comfortably defined as a wave. But the universe, it seems, loves a good plot twist. Fast forward to the early 20th century, when Albert Einstein was pondering a curious phenomenon called the photoelectric effect. Scientists had noticed that when you shine light on a piece of metal, it can knock electrons loose. If light were purely a wave, then a brighter, more intense wave should give those electrons more of a kick. But that's not what happened. A brighter light just knocked more electrons loose, but their energy didn't change. To give them more energy, you had to change the light's color. This was a puzzle that couldn't be solved with wave theory. Einstein's revolutionary insight was that light wasn't a continuous wave after all, but was quantized into discrete packets of energy. He imagined light as a stream of individual energy bullets, which we now call photons. A blue photon has more energy than a red photon. This perfectly explained the photoelectric effect. One photon hits one electron. A brighter light is just more photons, so it knocks out more electrons. To give an electron a bigger kick, you need a higher energy photon, a different color. Einstein had brought back Newton's particles. So, what was it? A wave or a particle? This is where the mystery deepens into something truly bizarre. Modern technology allows us to perform Young's double-slit experiment in a way he could only dream of. We can now fire single photons, one at a time, toward the two slits. We can watch them hit the screen behind. Each photon arrives as a single tiny dot, a particle. Exactly as Newton would have predicted. There's no wave in sight, just one particle hitting one spot. But if we let this experiment run for a while, letting thousands of these individual photons build up, something impossible begins to happen. Slowly, dot by dot, the interference pattern, the series of bright and dark stripes from Young's original experiment, emerges again. Think about what this means. Each single photon, traveling all by itself, somehow seems to know about the pattern that only waves should create. It's as if each individual particle went through both slits at the same time, interfered with itself as if it were a wave, and then landed on the screen as a single particle in just the right place to help build the wave pattern. The photon leaves the gun as a particle, behaves like a wave in the middle, and arrives as a particle again. Light was refusing to be just one thing. At this point, physicists were scratching their heads. How could a single photon possibly go through both slits at once? It defies all common sense. The logical next step was obvious. Let's try to watch it. Let's place a tiny detector at each slit to see which path the photon actually takes. Does it go through the left slit or the right one? This is where reality takes a sharp turn into the surreal. The moment we place a detector at the slits to find out, the game changes completely. The very act of observing the photon forces its hand. When we watch, the photon behaves perfectly normally. We find that each photon goes through either the left slit or the right one, but never both. It acts just like a well-behaved little particle. But then, when we look at the final screen behind the slits, we find something has vanished. The interference pattern is gone. Completely. In its place are just two simple bands of light, exactly what you'd expect from particles being shot through two openings. It's as if the photon, knowing it was being watched, abandoned its wavy, mysterious behavior and reverted to being a simple, predictable particle. This is the famous observer effect, one of the cornerstones of quantum mechanics. The universe, at its most fundamental level, seems to behave differently when we're not looking. When unobserved, a photon exists in a cloud of possibilities, a probability wave, where it can be in multiple places and take multiple paths all at once. But the moment we measure it, the moment we ask the question, "Where are you?" that cloud of possibilities collapses into a single, definite reality. The photon chooses a path. The wave vanishes, and all that's left is a particle. Let's explore another piece of this strangeness with something called the three-polarizer trick. A polarizing filter is like a picket fence for light. It only lets light waves vibrating in a certain direction pass through. If you take two polarizers and align their fences at a 90-degree angle to each other, one vertical, one horizontal, no light can get through. It's completely blocked. But now for the magic trick. If you slide a third polarizer, oriented at a 45-degree angle between the first two, something impossible happens. Light suddenly passes through the final filter. Adding a filter in the middle allows light to get through where it was once blocked. This happens because each polarizer measures the photon, forcing it to snap to a new orientation, allowing it to sneak through the next one. This strange duality, this refusal to be either just a particle or just a wave, isn't a quirk unique to light. This is where the story explodes from a curiosity about photons into a revelation about the entire cosmos. It turns out that this wave-particle nature is a fundamental rule for everything at the microscopic scale. Electrons, the tiny particles that orbit atoms and power our electronics, do the exact same thing. Scientists have performed the double-slit experiment with electrons, and they too create an interference pattern when unobserved and behave as particles when watched. The quantum weirdness doesn't stop there. This behavior has been demonstrated with entire atoms and even large complex molecules. Imagine a molecule made of dozens of atoms, a clunky object by quantum standards, being fired at two slits. Common sense screams that this bulky thing must go through one slit or the other. But no. Left to its own devices, it too acts like a wave, passing through both slits at once and interfering with itself. The universe, on its smallest and most fundamental level, doesn't seem to be made of solid, definite things in the way we experience them in our everyday lives. So, what is the answer? Is light a wave or a particle? The best answer we have is both. And neither. It is something else entirely, something for which we have no perfect analogy in our large-scale world. It is a quantum object. It reveals its particle face when it interacts with something, like when it hits a screen or an electron. It reveals its wave face when it travels unobserved through space, exploring all possibilities at once. We don't just see the universe with light, we see the universe in light. Its strange dual nature is a window into the fundamental rules of reality. This quantum reality is a world governed not by certainty, but by probability. It's a universe where particles can be in many places at once until they are measured. A universe where the act of looking fundamentally changes what is being looked at. This isn't just a fun thought experiment. It's the bedrock of the technology that powers our modern world, from lasers to computers. Light, our constant companion, our source of life and vision, holds in its heart the deepest and most profound secret of the cosmos. That the world is far stranger, more mysterious and more wonderful than we could ever have imagined.